Hello and welcome. Have you ever thought about the universe's ultimate speed limit? I mean, really thought about it? It sounds like a simple question, but the answer is, well, it's woven into the very fabric of reality itself. So let's dive in and figure out why it exists. So yeah, here's the big one. Why can't anything ever reach the speed of light? We can get things ridiculously close, right? We've pushed particles to 99.999 something percent of light speed. But we can never hit that final 100%. So what's the deal? What is physically stopping us?
Now, you've probably heard these two answers before. And look, technically, they're correct. The math checks out. As you get closer and closer to light speed, the equations say you'd need an infinite amount of energy or that your mass would balloon to infinity. But let's be honest, that doesn't really scratch the itch, does it? It doesn't give you a gut feeling for why. It's a mathematical result, not a physical reason. It doesn't tell you what's actually happening out there in space.
And that's exactly what we're going to get to the bottom of in this explainer. What is the actual physical mechanism that enforces this cosmic speed limit? And to figure that out, well, we've got to go back to the source. We're going to have a little chat with an idea from Albert Einstein himself. Okay, first up, a universal speed limit. The secret here isn't about having better engines or bigger fuel tanks. Nope. The answer is buried in the fundamental rules of space-time itself, and to really get it, we need to start thinking about time in a whole new way.
So let's talk about Einstein's photon clock. To grasp this universal rule, Einstein gave us this absolutely brilliant tool. It's a thought experiment that sounds super simple, but trust me, it is the key that unlocks this entire mystery. It's called the photon clock.
So just imagine this. You've got two mirrors, perfectly parallel to each other. And bouncing between them is a single particle of light, a photon. Every time that photon smacks into a mirror, that's one tick of our clock. Tick, tock. Super simple, right? This is our perfect fundamental timekeeper.
All right, now picture yourself on a spaceship, and you're holding this clock. What do you see? Well, you see the photon taking the shortest possible path, just straight up and down between the two mirrors. Tick, tock. Everything looks perfectly normal. This is your personal experience of time, what physicists call your proper time.
And here's where it gets weird. What if I'm standing still on a space station, just watching your spaceship zoom by? From my point of view, your clock is moving. So by the time the photon leaves the bottom mirror and heads for the top one, that top mirror has already moved forward in space. To catch up, the photon now has to travel a longer diagonal path.
And this is where Einstein's genius changes everything. This is the single most important, unbreakable rule in the entire universe. The speed of light is constant for everyone. It doesn't matter if you're the one moving or the one standing still. Light always travels at the exact same speed, c, always.
So, let's put it together. If the photon on your moving clock has to travel a longer path, but its speed cannot change, then what's got to give? Well, the only thing left is that it must take more time to complete its journey. So from my perspective, watching you fly by, your clock is literally ticking slower than mine. This is time dilation. Moving clocks run slow.
And I know what you might be thinking. This sounds like some kind of philosophical trick or a weird hypothetical game, but it's not. Time dilation is absolutely real. This is a measurable physical phenomenon.
We've actually done the experiments. Scientists synchronized a bunch of incredibly precise atomic clocks. Then they put one on a high-speed jet and flew it around the world. And when it landed, it was just a tiny bit behind the clocks that stayed on the ground, by the exact amount Einstein's equations said it would be.
But you know, the even cooler proof comes from the cosmos itself. There are these tiny particles called muons, and they get created way up in our atmosphere. Now, in a lab, a muon decays in just 1.5 microseconds. That is nowhere near enough time for it to travel from the upper atmosphere down to the ground. And yet, we detect them down here all the time. How is that possible?
It's because the ones that make it are traveling so close to the speed of light that they survive about 10 times longer than they should. From our point of view, their internal clock has slowed down to a crawl. They are literally aging slower because they're moving so fast.
And that just perfectly illustrates the point, right? If the ticking of our most accurate atomic clock slows down and the decay of fundamental particles slows down, then it's not just the clocks that are being affected. Every single physical process is slowing down. For all intents and purposes, time itself is slowing down for that moving object.
Okay, so moving clocks run slow. Time itself can stretch and warp. But how does this get us back to our original problem? Why does this stop our spaceship from just continuing to accelerate all the way to light speed?
Well, this effect isn't a gentle slope. It's more like a cliff. It gets exponentially more extreme the faster you go. At 50% the speed of light, the effect is pretty small. But once you hit about 87% of light speed, my clock would tick twice for every single tick of yours. Get to 99.5% and I'm seeing 10 of my seconds pass for every one of yours. You can probably see where this is headed.
So let's jump back on our spaceship. Let's say it has this incredible engine that applies a perfectly constant force. The goal is to increase its speed by 1,000 kilometers per second every single second.
Now, from the astronaut's perspective inside that ship, everything feels totally normal. The engine is humming along, pushing with the same force, fuel is burning at a normal rate. They feel a constant, steady acceleration. But for us, back on Earth, we're seeing something totally different. As the ship gets faster, its time slows down. Its second gets longer and longer compared to our second. So even though the astronaut feels like they're gaining 1,000 kilometers per second every second, we see them taking more and more of our time to get that same speed boost.
And this brings us to the final piece of the puzzle. This is where we finally uncover the real, physical meaning behind that infinite energy problem.
Let's just walk through the logic, step by step. 1. The ship pushes with a constant force. 2. As it speeds up, its time slows down relative to us. 3. Because its time is slower, gaining that next chunk of speed takes longer from our point of view. Its acceleration seems to drop. And 4, as its speed gets closer and closer to C, its time slows down so much that, from our perspective, the time it would need to gain any more speed stretches out towards infinity.
Okay, but that's the obvious question, isn't it? If we see the acceleration slowing down, why can't the ship just, crank up the engine? Just burn more fuel and apply more force to make up for that time dilation effect?
And that, right there, is the trap. Yes, you could increase the force, but as you get closer to C, that time dilation effect gets exponentially stronger. So to keep your acceleration constant from our perspective, you would have to exponentially increase your engine's power. To fight against time itself stretching out towards infinity, you would in fact need an infinite amount of energy.
So you see, the whole infinite energy and infinite mass thing, they aren't the root cause. They are symptoms of a much deeper truth. The real physical reason we can't reach the speed of light is time dilation. And the reason for time dilation is this one simple, universe-defining rule. The speed of light is absolute. It's the one thing that never, ever changes, which means everything else, including time itself, has to bend around.